Hello and welcome to Mr. Jackson's physics class. Today we're going to discuss light and color. Probably today we'll just get to the first part on light. What is light and how is it created? So let's start off with that idea. How is light created? Well, light is a wave. If light is a wave, that means we need to have something vibrating up and down to create these waves. And so that vibration is caused by electrons vibrating or moving up and down between the energy levels and then falling back to lower levels, okay? And so that is important to understand, because as it falls back to a lower level, then what's going on is we get energy giving off. So let's give an example here. So let's say we have an electron and we have our nucleus. Here's our nucleus right here. And we know that there are energy levels in an atom, and as energy strikes these electrons from maybe sun or heat or putting a piece of wood in the fire, what happens is the electrons jump up to a higher level. They're unstable. They want to return to their ground state, and as they fall back down, then they give off a wave of energy known as light. Okay? So it's the falling down of electrons as they jump between energy levels. That is how light is created, okay? And so that's what we need you to know. Well, why are there different colors of light and different types of light? Well, not every atom has the same spacing. Some atoms, like, we might have hydrogen, which has one electron energy level, but it still has other levels available to it, even though it may not be using those levels with electrons. And then you have other atoms like argon or neon or whatever, and some of these levels are spaced uniquely, sometimes farther, sometimes closer. It all depends on how their atom is arranged. And so electrons, when they absorb energy, they can jump up to some levels. Sometimes they only jump up to a single level, and as they fall back down, they give off different light. So one that falls farther is going to give off a different light. So maybe this might give off a blue light because that has a little bit more energy, and this one didn't fall as far, so its light may be a red type light. So the different colors of light that we give depends on how far they fall. So it is different because there's different spacings in most atoms, and they fall at different levels, and so their fall, how far they fall, I should say, gives off different kinds of light. You can even have electrons fall from extremely high levels, and they can even give off a different light, like UV light, which can then, it has so much energy it actually can pass into your skin and burn you, okay? So depending on how far they fall depends on the color of the light and the types of light, okay? So remember, if you need to take these notes and I'm going a little too fast, you can always stop the video and write your notes down, okay? So that is the best way to explain how different kinds of light can be created, okay? What is the scientific name for light? The scientific name for light is called electromagnetic radiation, okay? It means electrons moving around in a magnetic field. They then fall and then radiate or give off energy. So that's the real technical term for light, okay? Let's move on. Number 4. It says, what is a luminous versus illuminated? Okay, illuminate versus luminous. An object that emits light is called luminous. Okay, an object that light strikes and reflects off of is called illuminated. So if we were going to draw the difference between those, let's say that we have the sun. The sun is luminous, and I usually draw light as a straight line, not always as a wave, even though it is a wave. But then that light may strike the moon, and what happens is the moon can take that light and bounce off, but the moon itself does not give off light. It just reflects the light. So we see the moon because it takes light and reflects it back to us. So the moon, we would say, is illuminated, and the sun is a luminous object. It is one that actually emits or gives off light. Okay? Real simple. A light bulb would be luminous, and maybe your tennis ball in your room, okay, or your carpet would be illuminated. Okay? Now we have 3 words which are not very difficult, but they're kind of unique. They are called transparent, translucent, and opaque. Okay? Transparent are objects where light passes through really easy, and the objects on the other side of that material or substance can be clearly seen. A translucent object is something that light can pass through, but it either gets scattered or somewhat obstructed, so the objects that are on the other side are not as easily to see. Okay, and an opaque object is something that blocks all light. So let me give you an example. This glass right here would be transparent. So if I put a quarter in it, you can still tell that it is a quarter because you can see it really well. And so I pour it out, and so that would be transparent. This cup, however, is translucent. It has a bunch of scratches. It's older, but as I put the quarter inside, you can just barely see the quarter, okay? And you can hear it, you can see it moving around, but it is not distinguishable because the light doesn't pass through really well and it's obscured, okay? So that would be a transparent material. An opaque material would be a material like this cardboard tube. Light does not pass in there, so once I put the quarter inside, you can't see the quarter at all. You don't know anything's inside, but as I turn it, it's still there, and so it is an opaque object. Light cannot pass through it. So those are the three kinds of materials out there that we kind of can define, if that helps you. Let's move on. Number 7, what is the duality of light? The duality of light is that light actually acts as a wave and it acts as a particle. And that's kind of a unique thing. But tomorrow we're going to give you a video and show you how to explain that. It's kind of unique, but it's very important to understand that light actually has a dual nature. So they call it the duality of light. It can act sometimes like a particle and then sometimes like a wave, or sometimes both, depending on the situation. Okay? So that's the duality of light. Particle and wave nature or behavior. Okay? Then we want to move on. What is a photon? A photon is an elementary packet of light or particle of light. What it is light seems to come from the sun and other objects in packets of energy called a photon. So you've got to understand, as it falls from different levels, that photon might carry a little bit different energy, but they kind of have proven that light moves as a packet or a particle of energy. And they call that particle amount photon. So if you ever hear the word photon, they're just talking about light and light in some form, okay? I just want to give you that word for a definition, and so you understand in case that shows up in our reading or discussions. The next thing is, what is the speed of light? The speed of light is very basic. It has the same number, just like our speed of sound has the value of 343 meters per second. Light travels way faster, so much faster. Okay, and in fact it travels at 3 times 10 to the 8th meter per second. That's 3 with the decimal moved 8 places out. And we know 6 places is actually a million, okay? And so this is going to be 300 million meters per second, okay? That's quite a few. So let's do a problem, but before we do that problem, let's write down all the equations. Since light is a wave, light behaves with all 3 speed equations. Light can either follow distance divided by time. Light can also follow wavelength times frequency, because light has different frequencies. So you can have the red frequency, you can have ultraviolet frequencies, and so every type of light is also sometimes considered a different frequency. They can be measured in frequencies versus wavelengths. Okay, and then also speed of light can be found by using the wavelength and the time period for a wave, but that's not as common. We're going to probably be using these 2 equations a lot more, but I want to make sure you have all the speed equations, because light is a wave and it does follow speed, and it does travel through space pretty much at the consistent same speed, okay? And that is the speed of light, but this is only light speed in a vacuum, okay? That's the fastest light can travel. And anytime you put it through water or through glass, it's going to slow down and be smaller than that number. So that's the fastest light can go, but it has to be in empty space, okay? Or a vacuum, they call that. Empty space. So if you put it through materials, it pretty much always slows down. In fact, it does, okay? So let's do a quick problem. Let's say that we have a light or lightning. Let's say we have lightning. And this lightning actually occurs 2 miles away. and we want to know how long until that sound reaches us. So let's turn this into meters. This is roughly 3,220 meters. And we want to find out how long does it take time till we hear it. Okay? Well, we're going to use time. We know the distance, so we're going to use our first equation right here. And we're going to know that we're going to use the speed of light. So whenever you're using light, and we're going to say since it's traveling through air, air is mostly empty space. So with air, actually this number stays the same, but now water will change. So we're going to use this number right here to figure out how fast that light will reach us after it hits the ground 2 miles away. Well, let's plug our numbers in. We have speed, which is 3 times 10 to the 8th meters per second, equals distance, which we know is 3,220 meters, and we want to find the time. So how do we get x on top? Well, the best way to do that is to switch these two numbers. Okay, you can do that because I can multiply both sides by x and then divide both sides by 3 times 10 to the 8th. So if I wanted to do that, it would look like this mathematically. So these cancel out. And then I would divide these sides by 10 to the 8th meters per second. Times 10 to the 8th meters per second. And so what happens is I get this divided by this. So let's do that really quick. And remember your calculators, you have that power of 10 function on there. So 3,220, the meters, divided by 3 shift EE to the 8th, and it equals 0.000. This number is extremely small. That is 1.0, and I'm going to move the decimal, 1, 2, 3, 4, 5 times. So 1.07 times 10 to the negative 5th seconds. So that would actually feel or hear or sound like that the light met you at the moment it touched the ground, but yet it was 2 miles away. So light travels super fast, okay? Super fast. Well, what would happen if we were trying to time this lightning? Well, in a less than a second, you would see that light, but yet if we know the speed of sound is 343 meters per second, let's just change this number to the speed of sound. So you're 2 miles away, so 3,220 divided by 343 meters per second, it would take 9.38 or 39 because of the 7 seconds. So almost 9.5 seconds to reach you before you would even hear that thunder 2 miles away. But you would see it in less than a second, in a flash of time. So light travels much faster than sound. Okay? Just to give you an idea of how to use this speed of light. Okay. Let's move on. There are different kinds of light out there. So there is light we can see, there's lights we can't see. And so we want to talk about those things really quick. Okay, there are 7 categories of light. Okay? Those categories are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. Okay, these are different kinds of light energy that's available in our living spectrum of the world around us. Okay, we use all these different kinds of light as energy to do certain things. Okay, so we use radio waves, which is actually a light wave, to send out communication from radio and television stations. So the radio station turns their sound into a light wave, shoots it across the earth. That's why within moments, microseconds, it reaches your tuner, which turns it back into a sound wave. But it runs between the television station and the radio station, between them and our TV, as a light wave. And then our televisions and radios turn them back into visual colors and sound waves. So that's what they do for us. But radio waves are used to send communication around the world. We use that quite a bit in every town and every situation, okay? The next category of energy is called microwaves. They're a little bit stronger energy. We use those for cooking and satellite communications. A lot of your cell phones actually have either some radio waves they're tuned into or microwaves. So we actually send them, but you got to be careful. Some microwaves actually used for cooking are dangerous. So you know a microwave oven, but what they do is they make sure that the phones that you have don't put out a kind of microwave that actually can harm you. And so we do use that, but the more harmful ones can be used for satellite communication. It's okay to send microwaves up into the satellites and speak to them and change them, or like the rover that went to Mars, so it comes back quicker. We can use satellite communications because we're pointing it away from the Earth, okay, and not dangerous to us. But as we keep going deeper or farther down on this list, we're going to get more and more energy. Infrared is a form of energy that actually you can feel it. There are infrared plates, infrared heating. Infrared is a form of energy used for heating, cooking, and thermal imaging. Your body actually gives off heat. You give off thermal energy. And if I have a camera that can pick up infrared, I can see you in the dark because this camera would see the red light you are emitting. So you actually are luminous in some ways by the heat you give off. And some animals hunt at night by heat. They can see the thermal image coming off because they have eye bands or cones, I should say, forgive me, that are actually in the range of thermal energy. They can see things at night, like owls and snakes. Okay? The next band of energy is called visible light. It is what you can see. Invisible light is what we use for seeing. It's for giving us colors. It's also used in fiber optics communication. They send light through those little tubes, which can send information. So visible light is what your eyes are tuned to. Your eyes are not tuned to these three. We cannot see radio waves passing by, but we can see other things. Okay? And so, but we can see that. The next category is ultraviolet light. It's very important. We use that to sterilize and kill bacteria and water and equipment that are in hospitals. Your body takes in ultraviolet and makes vitamin D production. So the actual sunlight is very important for you to absorb, but you don't want too much ultraviolet because it's got a lot of energy. It can start to burn your skin. So we protect ourselves. We want some ultraviolet on a daily basis, but we don't want too much because it can cause a problem with your skin. But it's higher energy. And so sometimes they call it ultraviolet radiation because it's a little bit stronger form of light energy. Okay? And so you should know about ultraviolet and its uses. Okay? The next two categories are the two strongest ones. They are X-rays, which are used to examine sealed containers. So like if they want to check what's in a steel drum coming through a international barrier and they want to make sure it's not illegal or something they don't want to come into the country, they can X-ray that container and see what's inside. And we can also X-ray human body tissue, and it will go through, and not through the bones, but we can see if a bone is broken or whatever. And sometimes they use X-rays because they're so good at entering the human body, maybe to treat cancer. They can localize it and destroy the cancer cells with radiation. Okay? So those are very, very strong rays, and you don't want to get exposed to a lot of those. The last category is called gamma rays. They're extremely strong. We do use those in medicine. We do also use these gamma rays sometimes to sterilize certain things. Sometimes, ultraviolet is used for food packaging, to kill bacteria. It's in food too. And sometimes they do use these other ones too. And it's used in the nuclear industry to create energy and heat. But it's very under controlled circumstances. So these are the major types of electromagnetic radiation out there. Okay, and these categories have different uses. Okay, and the lower energy is more safe to be around humans. The higher ones we try to make sure are not exposing to human people because that can cause trouble. Okay, the last thing I want to mention tonight as I close is each of these has a wavelength, which means from peak to peak, and the longer wavelengths have lower energy. So this would be long, low energy, and they can be actually meters, if not up to half a mile apart. But then as you go to microwave, the waves get closer together. Okay, and then as you go on, of course, then you get to gamma rays, which are extremely close together, and it has very, very high energy. So I just want you to know that as you decrease the wavelength, you increase the amount of energy it's carrying. Okay, so that's how wavelength and energy are related when it comes to light, forms of light energy. Okay, thank you for joining me for this discussion on light and the types of light, and all the ways that light is being used and explained with luminous and illuminated, and how light is created. Okay? Have a great day. Take care.